Hello everyone, welcome back to the Oak Island Research channel for a new video. That's I'm very excited to show you what's in there. And I just spent 1 hour with my friend Ed Hyde over a team session. We've been sharing ideas about this little piece of apparatus you see on the screen here, and really wondering what it is and what's the purpose of it. Let me just do a quick check, making sure the video is being recorded. Yes, it's okay. So pretty sure you can see and hear what I'm gonna show you. The Volt incredible mechanism, because it is what it is. Remember the last video where I was making hypothesis about what this could be, and Ed Hyde sent me an email a couple of days after saying, very interesting, I thought about it, this is my proposal to you about what it is, how it operates. And I didn't fully buy it at the time. It took me many weeks of thinking, 3-4 weeks. And 2 days ago I had a kind of a flash. I'm saying, okay, now I know what it is and how it works. And of course, Ed was somewhat right, or his proposal makes total sense. And I'm going to embed my vision and his vision into what this apparatus is and how it contributes to the operations of the Volt. Very excited, because I think we're on the right track, and this one was not obvious, and I hope you're gonna really enjoy what we're gonna show you there. Okay, why is not talking to Michael anymore? What's up? Ed has been sending emails in the past on my account, and Ed has a background of engineering. He's a proper engineer. I'm not. I'm an engineer. I got the degree, but I'm not that of a technical, mechanical guy, more into the business side. But Ed is there, and as engineers, if we think that this apparatus is an apparatus, it's not a boat, or maybe it was before, but it's not now, an engineer would ask himself the question, what's the purpose of this thing, and what problem does it solve? Because you don't spend time, effort, and money building something if it doesn't have any purpose. So that shape, which is on the Rochefoucauld map, meaning that shape's got something important about it, has got a purpose. And as engineer, trying to discover what was the purpose, that would indicate a lot about how this system works. And one thing that convinced me we're on the right track 2 days ago is I had a kind of a flash or revelation. And I was thinking, okay, they built that Volt mechanism. We know that when it's protected and you're not supposed to access it, the service tunnel doesn't connect because there's water underneath. And the water underneath is trapped by this plug at the back, which is called the valve, la soupape on the Rochefoucauld map. And on the other hand, it's locked here, so it makes a tight container, if you want, and water is trapped. Why is it trapped at this level? Because you block your mechanism at high tide, and the high tide level make it that your Volt chamber is up, and you're locking everything so that nobody has access. That's the position of the locked Volt. And my problem is, how do you make this watertight, water sealed for 1,000 years? When they designed that thing, they knew they were not going to come back and service it every year. They knew it had to stay there for quite at least decades, if not centuries. And whatever they did, they understood that you cannot trap water inside at the pressure you want, which was the high tide pressure at the time you trapped the water inside and you blocked it. Now the ocean's going up and down, and when the ocean's going down, you don't want that water to flee and to evacuate. So you need to enclose it, trap it. But what about water leakage over the years? Because if on the 1st of January you did your mechanism proper and you trap the water, come back 100 years later, I'm pretty sure the Volt will be back on its resting position and anybody can have access to it, which is not what you want by design. By design, if you block and you lock the Volt at the high position, you want it to stay there forever. And forever is a long time. So as an engineer, the question is, how would they solve the water leakage problem to guarantee the vault is safe hundreds of years after they last operated it? That's the question. And the answer is in that little apparatus. So that's going to be quite a journey. Let's deep dive more into our leakage system, leakage problem. So there are 3 areas where the water could leak. It could leak at the entry from the ocean, it can leak at the back, and it can leak probably at the entrance here. Let's deep dive into each of them. As you can see, the valve has got 2 specific devices on it. It's a screwed shaft, a threaded shaft. It's got like a screw, meaning that you can exert force on it. You can exert vertical force on this thing, which seems to be multiple layer, almost telescoping one arm getting into the other. I mentioned that in a video a long time ago. I asked my dad some years ago about how would they make waterproof in the Middle Ages, and he answered me they used leather coating all around, and you put that shaft down and you force it with the screw. That's the valve, la soupape. And by doing this, you're going to compress, probably that's how they do it, compress leather in there in quite a narrow, it's probably narrower than what they show. Why? Because the narrower, the easier to seal. If you get a big duct, you're going to have problem for the waterproofing. So Ed and I think it's a restricted type of smaller exit, and it's easier to manage the leakage or the non-leakage of this. So this is more or less covered. They found a way, but I doubt that over 1,000 years this thing was fully 100% waterproof, watertight. So we'll talk about this again, but that's one area where potentially you could have a leakage. Small, tiny drops per year maybe, but drops per year out of 1,000 years makes a lot of drops. In the middle, the service shaft, which you enter, and you can see here there's an opening. So I don't think here there's any water leakage, because what Ed and I believe is that the maximum level of water you can get will be here. You will not get any higher, otherwise you would flood yourself. Meaning that this line is the high tide water level mark. You will not get any higher than this, otherwise you would first flood yourself, and if you had any door or whatever, you would not sustain the pressure and you would leak. So if you're making this move up and down, it's very hard to make a sliding slide against slide waterproof system. So we think we're right, and the water doesn't go above this level, and this level is the high water mark, meaning that probably that thing compared to the soil above is not very deep, because basically that's the surface, that's the high tide mark, and that's how deep you have to dig, which is not a lot. Actually, that's that deep you got to dig. So probably not buried very, very deep. If it was very deep, you would have water all the way to the top with a lot of pressure pushing on this, probably destroying because of the high pressure. So we really think that's not buried very deep. And I get back to this, or actually I can get back to it now. I was a little curious about how deep it was buried. And I'm going to show you something. If you go on Google Earth and you're going on the west part of the island, you've got at the bottom right here, elevation, E-L-E-V, elevation, bottom right of my screen, in meters. I'm sorry, I'm French. European, doesn't matter, multiply by 3, you get a number of feet. And of course the water is at 0 meter, thank God, that works. The swamp is at 0 meter, and here on the left hand side, check this and track my elevation. I'm going on the left, 5 meter, 15 feet, 12 feet, 6 feet. There's no way you can hide a chamber there. You're gonna hit the bed, the water level, the ocean level right away. 4, 5. What's the highest elevation? What's the highest place on the island? Let's go back to where Michael finds the vault. Here we're at 7 meters, 21 feet, 8 meters, 24 feet, 9 meters. That's that area where the vault is around. That's the highest point on the west part of the island. 9 meter, trough one of 27 feet, and 8, and all that is like a plateau, like a high plateau, 7, 8, 7, 8. If you go on that side, you're going down back 7, 6, 5, 4 meters. If you're going on lot 5, 8, 7, 7, 8 again, 7. I'm around where the hole under the trapdoor is, 8. Where the valve is supposed to be, 8. So it seems they found an area where everything is like 8 meter high, 26, 28 feet, 27 feet. Maybe that's what it is on La Formule. 27 is the value how deep the vault is. Maybe that's what it is. And 27 feet is what you get on all that portion I'm circling. So that's the best place on the west side of the island to put a vault and to put the trapdoor. If you're having your hole under the trapdoor and the valve and you don't have enough island soil, you couldn't put your ducks. You would be at the ocean water level already. So you need a bit of soil to work your ducks and work your apparatus. So it makes total sense. They chose for the hole under the trapdoor and the valve, they chose that part of the island and the vault around here because that's the highest elevation you'll get. Of course, on the east side, it's another story. It goes way higher. It goes all the way to 11 meters, 12, at 36, 39, 42 feet, 45 feet. That's what you get here. But on the other side, they picked the place where they could install that vault mechanism. So it's not very deep, I think. On the hump, on the right-hand side, again, you're going to have the ocean pushing, and if you want to flush your water out to access the chamber, you're going to have air here. And that's a lot of difference between an ocean pushing on a door and air. So here again, you can have leaks. On the other hand, when you lock your mechanism, you have water tight, trapped at high tide pressure. And here you can have low tide, for instance, and the water will force on those slides. So you can have leakage again. What I'm saying is over hundreds of years, there's no way the water at high pressure trapped in the vault would have stayed for 1,000 years there. It will have escaped one way or another. So that brings me another question. Those people were not stupid. The guys who designed that mechanism were genius, and they must have found a way to either keep the water in, which is not possible, or have an automatic refueling, replenishing, refreshing. How do you say in the States when you get free refill? That's what you get. You don't have that in Europe. Free refills on your drink. And this is what you got there. And I'm going to explain you exactly how it works and how brilliant it is using that little piece of apparatus that is shown on the Rochefoucauld map. So let's start. This is the layout of the island we're going to work with. I sketched the best I could, and that's not very good. I'm better at telling stories than drawing. So you got the island and the trees on top. You got the ocean. The high tide water level is in blue here, which corresponds, of course, to this point, which is the highest you can go. And you have your 5-finger drain. I only drew 3 because it was a bit of a pain to draw. So that's your water intake from the ocean. And this is if you got the oak entrance here, and at 45 feet, you got to dig east, and on 522 feet, you're going to enter this corridor. And this corridor here is 1044. I can't remember the exact name, but this one is 522, according to La Formule. Ancient French feet. And you will enter that chamber, which is the hump chamber, where you've got that hump there. I put it in orange. I'll explain you later this mechanism and the orange part, but that's where your hump is. So your water is coming, and it's coming into that specific place here I'm going to describe and help you with. And the water carries on all the way to the chamber. And if you got the same water level as the high tide, of course, you're going to have water all the way through here, and it's going to push the box or the chamber up to its locked position. That side will work. At the back of the apparatus, you've got the valve with its screw we just saw, and pouches of leather, probably blocking the water and keeping the water in, or if you adjust it up, it will let the water out. Okay, that's the layout and that's the design we're going to use for the upcoming slide. So that's the setup, and it's the same setup as this. I just reorganized it for, I don't need the money pit, I don't need the hole under the back door. I just describing functionally how it's going to work. Okay, the valve. This is the top picture zoomed of the Rochefoucauld map and the bottom picture of that apparatus. And I reproduced it here on the left, what I saw and understood. I would like you to notice something very important. The way they designed and they drew and they took attention to, they did not do a rectangle and a triangle. That's not what they did. If you look at here, the triangle here, it's less obvious, but here you can see there is a return, a right angle first, right? Here you can see it again. Here you can see it again. So what they did on the drawing, they made the triangle smaller than the rectangle. I'm exaggerating it, but you can see it definitely here. Here, the end of the triangle is different from you get that little right angle. And here you don't see it very well. Maybe they screwed up when they did the marker black thing, whatever, but definitely it's here, and it's here. So I drew it because it's very important. You'll see why in a second. So that's my model of what is sketched on the Rochefoucauld map. That's the original sketch. And today, I went back to it and I had a hypothesis I wanted to verify, and it verified very well. I say this is the same device twice. They show it in two different positions. It is not two items. It's the same item depicted in two different status. And as you can see at the bottom, if I isolate, if I take this as a reference, the little dent here, the little tooth, and the little tooth, I'm drawing a vertical line, and I realize the same vertical tooth is not there on the copy on top. It's offset. I do it on the second, offset again. I do it on the third, still offset. Like the boat or whatever this is moved. And I did the opposite. I took the bottom marker, and it doesn't correspond to anything anymore. I take the bottom marker here, and it doesn't correspond to anything anymore, and etc. Meaning the boat, or whatever you call it, moved between the lower position when it was in la barque state and the top position. It did move. What made it move? La hampe, of course, because la hampe is here. And it's la hampe. As you can see, it's bent little bit. It's not a straight line. It's got an angle. And la hampe is what is causing the change of position, as you can vertically compare. So let's take that. Let's note that on the back of our mind is that la hampe is connected to those devices. Okay. So let's do a step-by-step scenario. You are at the high tide and you want to lock the vault in a safe position so that no one can access the vault. So here in the ocean, you got the maximum tide level. The ocean is at this level. And the water enters the 5-finger drain, enters the ducts, and enters this chamber. And at this very moment, our plug, let's call it the plug, the green thing. Our plug is buoyant between two waters. I check with Ed. Yes, that's almost English. That is, it is not floating and it's not sinking. It's halfway between. If it was sinking, it would have contact between here and here. If it was floating, you would have contact on the top. We don't want any contact. So we think the buoyancy or the density of this green plug is the same density as the density of seawater. And I can't say that top of my head the number, but it works if you use it this way. So they had it, and maybe it's a boat that they fill with water, or a bark that they fill with water. A bark would float, but if you fill it with water, it becomes unbuoyant between two buoyant stages. Okay, so you got your water, and because nothing is blocking the water is going through here, and then there, and then there, and is free to enter the vault. At what pressure? The same pressure as the ocean water. So the elevation will be the same as the ocean elevation, which is the high tide marker. So your box, your chamber, is installed in the upmost position, and at this very moment you will lock your backflow valve so that the water stays in. And let's remember, this is exactly at the high tide. It's at the slack, we call it, I think, the slack between the two tides, when it's at top tide but hasn't started to go down yet. And that's the position of the mechanism. And now we're going to see the very first minute when the water is going to go down. So again, I'm just isolating this. You got the green plug. The green plug is not touching anything. It probably got a guiding axis here, a shaft or a guiding axis. But other than that, it's at the same buoyancy as water. Therefore, it's not trying to surface. It's not trying to sink. It's halfway between, and it's free of move. It can move freely. Now the tide is slowly starting to go down again. Let's remember the situation. I've got enclosed water here. The water cannot escape because I got good sealing properties. And my elevation of water at the very moment the tide is starting to go down is at the high tide max. And of course my tide is slowly bringing my water down. And of course the water in the vault is following the move and trying to go and level the same as the ocean. So it's trying to go that way. The water will slowly go down because the elevation is going down. And by that flow, the water is going to push. Let's see. I think it's animated. So this thing freely moves, right? The green part freely moves. And then all of a sudden, I've got a water current. Water going that direction with velocity, small velocity, trying to escape and rejoin the water level in the ocean. So what's going to happen to the green thing? The green thing is going to be pushed, to be pushed, to be pushed, to be pushed to a certain position where it cannot go any further. So the more differential of water you've got between the ocean and what is in the tank, the more pressure you're pushing and making sure you get sealing and water is not escaping. Plus the nozzle shape, the triangle shape, makes it a very, very high surface area of contact for water sealing. So it's very interesting that when the water is going down in the ocean, automatically the green plug will position itself to deprive any water from going down. And the more the water wants to go out because of the pressure differential, the more it pushes and self-lock this device, this plug, that does not allow water to flow out. So the more you push, the less water you get out, which is absolutely brilliant from an engineering point of view. So that's one thing. And as soon as the water from the ocean is going to start to go down, the apparatus within a minute or two will start touching this, and the more pressure differential, the more stuck to the right hand side it is, and the less water will get through, maintaining the high tide water level in the vault, minus a couple of centimeters or inches. So that's awesome, isn't it? It self-locks when the tide goes down. My problem is, let's remember, I may have tiny drops of leakage. Water wants to leak everywhere. Waterproof is not awesome when you got ocean pressure. So they must have thought that after a cycle or 2 or 10 or 100 or 1,000, you would have water leakage. So this is what they did, and that is the most brilliant thing ever. So the vault leaked some water, and now, this is my high tide water level. I was there, but I'm leaking. So now my elevation of water is just there, and the vault is a little bit under, but not yet to the point I can enter it. And we don't want people to enter it. But I lost water. The ocean every 6 hours and so, has got those tide cycles. So the tide is going to start to go back up. That's a God's pump, right? And at one point in time, it's going to go back up at the same level of what's left in the tank. And at one point in time, and remember this green thing is stuck to the right, depriving any water movement. And at a moment, this elevation will be higher than what's left in your tank. So the pressure is reversed. Now I got high pressure here, and I got low pressure there, compared. There's more water, and here there's no water, so it's pushing. So what's going to happen to my piece in the middle? My piece in the middle is going to be pushed by the opposite flow of water than before. My flow of water wants to go that way, because I got tons of pressure pushing here compared to the pressure here, represented by this blue box. You're taking a crash course in fluid dynamics, aren't you? And this is moving, and this will slightly push the green thing to the left. And what happens when the green thing is on the left? Well, everything is open, the water can flow back in, and the water will replenish automatically to the same level, up to the high tide, and here I am again. There's the slack, the thing now is free, both pressure same, and here we go again for a cycle. Water going down, the green plug goes to the right, trapping the water on the left, losing a bit of water in the process, a bit of leakage. Fair enough. At the next high tide, the thing is going back to the left, and the high tide water will get back and every 6 hours replenish the vault, so that the vault is always at the top level. And it's been like this 2 times a day for 1,000 years. And it probably still works, because it is so clever. It doesn't require any human action or anything to replenish every 6 hours, every 12 hours, sorry. You get 2 high tides per day, per 24 hours. Every 12 hours, you've got your vault, water, level, replenish to forbid the access. And you're not letting that caisson box going down, because your leakage of water through the gate, through the poor sealage of the leather or whatever. That's how they did. That's for sure. I mean, you cannot have a hydraulic mechanism that withstand the pressure of the water in it for 1,000 years. It is impossible, even nowadays. So you need to think about, how do I refill the water? And you need a pump. You need something to force the water in. Well, you've got your pump. It's called the ocean and the high tide. And it's a beautiful, marvelous Swiss clock pump, because every 12 hours, you're going to replenish everything. This is just brilliant. And it's because of the shape of that object that you're allowed to do it. But why does it have this nozzle and that very important right angle here? Because if you didn't, and you had something that looked like this, for instance, instead of that cone, well, then that would be my duct, right, that I'm trying to plug. Meaning that to be able to have water out, I need to fully remove that thing so that it looks like this. And now water can drop down. But you don't want that, because you can't push that forever on the left. The beauty of the nozzle shape is that if this is my entry of water, as soon as I move one portion of an inch to the left, water starts flowing because of the shape of the triangle. And that's beautiful to have thought of it. That's the most perfect shape to do that. I was talking to Ed, and I was saying, this looks like a jet engine, actually. But it's 1,000 years too early to talk about jet engine. But whoever designed this, he's a freaking genius. Now, I want to show you something else. When the water leaks, when the water is going back in, if you are not careful and you end up in this position here, you're going to, okay, the water can get through here, no problem, can get through there, and then cannot enter anymore. So you're not allowed to move your green plug too far to the left, otherwise you're going to seal again, and you don't want to seal because now you want the high tide from the ocean to replenish your tank. So they must have put a stopper, a way of saying you're not allowed to go any further. And those stoppers, let me zoom for you. That I drew them like this. Here they are. And those will allow the green plug only to move to this position, allowing the water, oops, sorry, excuse me, this is live, allowing the water to pass through the gates, through the teeth, and go down with the pressure. And this ensures you're not blocking the water on the opposite and contrary move. Brilliant. And that's probably why this little thing here is probably it's inside a cylinder for to have a guidance guiding the movement. Remember, it's buoyant. It's not buoyant. It's in between two waters, so it's free floating. So you need a guide to allow it to go left and right without failing, or without for 1,000 years that it can operate. That's fascinating. I mean, this design allows so much things from a hydraulic point of view. I've never seen anything like this in my studies, or this is a brilliant it's almost robotic, because it reacts and does its function without a man, and it without a human presence, and it compensates like I mean, it's brilliant. I'm so impressed by the design, if it is what it is, and I do believe it is what it is. Let's carry on. So now I need to access the vault. I want to go have a look at the treasure, if there's the treasure. So now I need to block the ocean from entering. I, of course, need to raise up the valves to let any water out flush into the hole under the trapdoor here. There's an underground cavern, probably an underground cave. But I want to be in there. I know the water is going to flow out, but I don't want to let any water in, because the purpose is to block, is to stop the water from the ocean entering and to flush out the water in the vault. And I don't want to get, drawn inside that thing. I don't want to be in contact with the ocean water. It's too powerful for me. So this is when La Hampe come into play, and I'm going to show you my model of La Hampe, and I'll explain you what Ed is thinking, which is not exactly the same approach and use of the Hampe. So I need to lock this green thing into locking position, no water going inside. But here, I could move that thing to the left. That's why I'm having this apparatus here, which is a rod. And when La Hampe rotates, it rotates this cam. I'll zoom it. And the cam will push the orange rod into contact with that green thing, locking it in position. It cannot move anymore. And if it cannot move anymore, any water cannot, and even if it did, it's blocked again, and if indeed blocked again, and there's no ocean water that's going to come under pressure into my tunnels if I do this. So what is this? This is a cam. This is a French drawing, but forget about the name, except this is la soupape. It's a valve. It's another form of valve, and that's your Hampe. That's La Hampe here. L'arbre à cam, that would be La Hampe. And when you rotate La Hampe, you rotate this non-circular piece. And of course, when that non-circular piece rotates, at one point in time, the bigger part here will be in contact and will push the valve outside of its lodging place, its housing, with perfect seating here. That's an engine, of course, nowadays. And that's how it works. If you rotate that thing. So a cam is used to convert a rotation movement into a transverse movement. I'm making the Hampe rotate, and this thing is going up and down. That's what it's used for. And I did a bit of research at the bottom. The camshaft also described in the late 12th century and coming from the 11th. So it works in our temporal context, because I still believe Rochefoucauld Map is talking about all this, and Rochefoucauld Map is certified 1280. So we are right in the right era, and originally it's for the windmills or the water mills. They would use that rotation and want to turn it into a horizontal, especially for hammering. Hammers, huge forging hammers, they would have the rotation movement from the water mill and need a vertical up-down movement for the hammer to hit whatever it had to hit. Okay, so now, so again, what do I do when I want to enter the chamber safely. So this is a description of the two stages. Unsafe, meaning the vault is at the top position, meaning there's a lot of water at the water high tide level. And I need to freely let the green plug go left and right according to the tide cycle. The ocean's going down, well, then the pressure in the vault will be higher than the ocean if it's going down, and it will move that plug here, blocking every water from getting out. Then the water is going back up. If I lost water in the tank and in the vault, the extra water on the ocean will want to enter the vault to level the difference of pressure, and this thing will fully move to the left. Careful, not too much, otherwise you're blocking everything. That's why we have those two stoppers. And this thing will go back and forth according to the tide cycle, either blocking water from escaping the vault or replenishing the vault automatically in case you lost water. And if I want to enter the vault and block everything and control the ocean from not coming, even during any cycle, I just turn la rampe, I turn the cam, and that will force that yellow rod pushing my green plug and locking it in this position, not dependent on the difference of pressure anymore. I'm going to end up having air here and ocean here, and I need a very strong way of blocking the water and its pressure entering, and that's why this rod makes it in a very, very steady position. We use that in petrol engine nowadays, and that's how a cam works, and it's a lot of pressure it's taking. Ed Hyde has got another proposal. He said, without the cam, you can directly put your hump right in there, or put your hump right in there. So according to where you put it, you would deprive the green thing from moving any further left or moving further right. So the hump may just be a blocker, a vertical blocker that inserts between the teeth of the apparatus, which could very well be, because when you look at the way they drew it, they drew nothing but a kind of an arrow with a more rectangular end. That's what I see here. And maybe it's just something you would block in your little shuttle, the shuttle that's going left and right. And what they didn't draw is the teeth and etc. and etc. Maybe. I don't know. We don't want to fight with Ed, of course. We both have our points of view on this. I like my cam mechanism. It's more complex than a direct hump pushing into it. But at the same time, we don't know. So both could be true or both could be wrong, actually. But again, if this is really the purpose of that device, and if it works this way, which actually solves the engineering problem, how do I compensate leakage over 1,000 years, then this is brilliant, first of all, absolutely incredible from an engineering point of view at the time. And if this is true, then the Rochefoucauld map is not a hoax. How can you imagine in your hoax something as sophisticated for this purpose? And waiting for two stupid guys named Ed and Olivier to figure out how this would work in the context of other documents such as the Scrolls of Antera. I mean, come on. If it is what it is, and it is what it is, I think, really, then it cannot be a hoax. You cannot figure it out for a hoax. Or you're a freaking genius and you shouldn't do hoax. You should do movie screenplay or something. So yeah, that's my cam, that's my valve, and I'm pushing it according to, do I need to let it free of movement? And or do I lock it so that I'm safe and no ocean water will ever come in the tunnel once I flush it? I am incredibly seduced by this apparatus and the way it solves the problem of water leakage, because I don't see any other way of solving it. It is very elegant from a mechanical engineering design point of view. It is brilliant. It's a genius. And I salute whoever in the past came up with that design. Da Vinci, I don't think so. He was not born. But, you know, there are smart people on Earth before Da Vinci. But to be able to, there must be a model somewhere. I was thinking about this afternoon. I was going to make a model of the whole island in my living room. And then I gave up as soon as I had the idea, because, oh my gosh, But that would be an incredible way. And again, let me recommend on the back and forth. Beautiful, replenishing, automatically replenishing, and automatically plugging it based on the pressure difference. This is mind blasting because it's so elegant, it's simple. Anyways, you understand, I'm very excited about this because it solves several problems. The leakage problem, the what it is they drew on the Rochefoucauld Map problem. And I thank again Ed for his patience with me and for his engineering insight that really helped me. And I thank you all for watching this. Thank you very much. Talk to you soon with new adventures. I'm really keen on looking at your comments and see what you think of this. Everybody have fun and be safe. These are hard times nowadays. Take care, everyone. Bye-bye.